This brings us to the next session, a training workshop that we have. Since morning, we have talked about centrifugal pumps. We have talked about, vertical pumps. We have talked about submersible pumps. Our next training workshop is going to be an introduction to airlift pumps, their pump curves, and their various applications. And for the workshop, I would now like to invite Paul Subject, CEO for Flonergia, and Josh Rossetani, applications engineer at Flonergia. So over to you, Paul.
Thank you so much, Kailash. It's a pleasure to see you all today and to be joined by my colleague, Josh Rossetani. It's early morning here in Canada, and just to give you a bit of a weather forecast, we've had a bit of snow overnight, but it's lovely to meet you all today. I will be sharing a presentation about airlift pumps in general, where they came from, what they're made of, and I will also then turn it over to my colleague Josh, who will talk about how to deploy airlift pumps. So I'm going to share my screen. And Josh, give me the thumbs up if you can see that.
Yep.
Thank you. Okay, so a lot of people have run into airlift pumps before, and we thought that this would be an ideal opportunity to talk about where they come from. So what are airlift pumps? There's a lot of misconceptions about airlift pumps, and there's a lot of homemade products that are out in the marketplace. If you go and look on YouTube, you'll find all kinds of very interesting things that people have built. The original airlift pump design has been around for about 100 years, and the figure I show here off to the right shows a US patent that was filed back in the early 1900s. Initial designs injected compressed air at the bottom of a discharge pipe. And because of the buoyancy of air and water, this discharge pipe and this air would lift the water up the discharge pipe and discharge it at the top of the pipe. And this has caused, the physics around this is fundamentally quite simple. It's based on the buoyancy of air and water, which lifts the water in a pumping action. And at the same time, solids, a certain amount of solids can be commingled with the air and can be pumped simultaneously. So the energy footprint of these pumps is quite interesting. If you think about then that the only motive power is the compressed air, then the energy to deliver that air is the thing that actually drives the pump. There's no separate electrical motor running rotating mechanisms. And by buoyancy, the air, which has a low density than the liquid, of course, it causes the liquid to rise fairly quickly, which creates the pumping action. And in terms of fluid pressure, the liquid is taken in the ascendant airflow and moves in the same direction as the air. So the physics is quite simple. And the calculation of the volume flow of the fluid is possible based on the physics of this two-phase flow. So what are the advantages of airlift pumps? Well, they're very reliable. There's no moving parts except for the delivery of the air. Liquid being pumped is not in contact with any mechanical elements. Therefore, the airlift pump is not abraded by anything that is abrasive, sand, debris, etc. And additionally, depending on how the air is delivered through the airlift pumps actually act as water aeration devices and can lift stagnant bottom water to the surface. Now, since there's no restrictive pump parts, solids generally up to 70% of the pipe diameter of the pipe of the airlift pump can be lifted. All very good, right? Problem is, there's some disadvantages to airlift pumps. Compressed air required for most airlift pumps is expensive to produce. Suction can be limited depending on design. And airlift pumping systems are only suitable if the head is relatively low. And lastly, but certainly not leastly, there's very few of commercially available airlift pumps. If you search on the internet, you probably won't find any except for one. And because of this, that there's very few commercially airlift pumps available, this has occurred because the lack of design optimization over the last 50 years shows that there's no real advantage using airlift pumps. New innovations that are out there now have started to solve some of these flaws in the original design. And of course, our company has completely re-engineered the airlift pump to solve a number of these issues. So I'd like to talk a little bit about our technology. Our company was incorporated back in 2016, and the technology that we have commercialized was developed at the engineering department of the University of Guelph in Ontario, Canada. Our patent pending technology is currently being sold to aquaculture, agriculture, and wastewater markets around the world. And in India, Everest Turbo is our exclusive distribution partner. Now, as you know, you've been listening to people talk about pumps all day. The challenges with pumps is that the cost to move water is high. Pumps generally are expensive and use a lot of energy. Parts wear and maintenance clearly is a challenge, and aeration is expensive and inefficient. And as we all know, the life cycle cost of a pump and its rotating systems are many times the initial purchase price. So how does our technology solve these problems and the problems in general of airlift pumps that were designed more than 100 years ago? Well, our technology only uses the aeration alone to both pump and aerate water. So the energy you use to drive your aeration system or your blower is what's needed to run our pump and aerate the water simultaneously. This reduced energy profile results in a 50 to 70% energy savings because we're removing the conventional pump out of the system. Our airlift pumps have no moving parts, and as a result, they have very little maintenance. Our airlift pumps have exceptional aeration properties versus conventional systems, generally up to 40% better aeration efficiency versus paddle wheels and surface sprays. So what's different? Well, Josh is going to talk a little bit about this in greater detail, but our pump has been optimized using computational fluid dynamics to flow and to aerate simultaneously and to optimize the multiphasic behavior of the pump so that it maximizes the output, but also maximizes aeration. Additionally, we used finite element analysis to design the pump to ensure that the pump will withstand the operational stresses that we experience on a daily basis. So essentially, our airlift pump is the first engineered airlift pump system that's on the market. And what does this do? Well, by removing the actual centrifugal pump and the power to run it, and to remove the paddle wheels and the power to run those, and to combine those into one system by using a standard regenerative blower, our system, essentially with no moving parts, very low initial cost and extremely little maintenance, and a reduced energy profile results in pumping simultaneous with aeration. And of course, we can pump solids, liquids, and solid liquid mixtures. And you can see a cutaway version of our pump here on the right-hand side of the screen. And at the top, you see where we inject air, which creates a piston, or what we call slug flow, of air that lifts the water. And the bottom port is where we inject air to enhance oxygenation and aeration. So by using the power required from the air itself to generate the airflow and from the blower, we lift and aerate simultaneously. So there's no additional power need to pump water. And this results in a 50 to 70% energy savings, 40% better aeration efficiency, and substantially reduced maintenance, essentially zero. So talk about some applications, and Josh is going to talk in greater detail about some of these applications. Our pumps can be used throughout every operation where you need to move water from one location to another. But I've chosen wastewater here because it's an easy application for our technology. So we can be used to transfer pumps from one location to another, transfer fluids, to pump heavier materials, and to deal with sludge. So looking in greater detail, if aeration is required to improve flocculation in a waste stream, our pumps can do that. To transfer from one tank to another tank, our pumps can do that. And to transfer heavy sludge, heavy materials, and Josh will talk about the materials we can pump with our technology, our pumps can do that. So some additional features and benefits. As I said, our pumps can easily move heavy fluids and solid waste. We have no moving parts. It's very difficult to clog our pumps. As a matter of fact, we pump fish in the aquaculture business. Our pumps are fabricated from food-grade polymer and can't be corroded. Our pumps facilitate carbon dioxide removal if that's a necessary part of your process. Our pumps disrupt thermal stratification because of the upwelling nature of how our pumps work. And our pumps improve dissolved oxygen. And we have pump capacities in a range up to 2,685 liters per minute, which is 44 liters per second. Spend a little time talking about our size range. Of course, we have pumps up to 8 inches in size, and the 8-inch size is the size of the pipe that the pump uses. Our smaller pumps, we have a small 1/2-inch pump, which is used by aquarium people. Actually, it's it's a very cute little pump. Josh, do you have a 1/2-inch pump there that you can hold up?
Probably not with me here now. So.
Okay. As you can imagine, it's about as big as your finger. It's a great little piece of technology. But our 1/2-inch, 1-inch, and 2-inch units are printed in 3D food grade polymer. And our 4, 6, and 8, and I have the 6 and 8 here beside me. These units are made of standard PVC piping material, and they're fabricated. All of our pumps are currently manufactured here in Canada. Spend a little time on our pump curves. So these pump curves are a little different than probably what you're used to seeing, but these pump curves really show the airflow rate across the x-axis and the resultant water flow rate across the y-axis, both in liters and in gallons per minute and in cubic feet per minute and liters per second in terms of airflow. And Josh is going to spend a bit of time talking about the efficiency ratio, which we call the submergence ratio. But you can see the curves here for each one of our pump sizes. And essentially, at the 50% submergence ratio, our pumps start to work up to the 90% submergence ratio. Below 50%, our pumps are not really that effective. So, but Josh is going to talk more about how you read this curve and when you use this curve in a few moments. But the top rate, as I said, this is the airflow required to operate the pump, and this is the resultant output on the y-axis. Just to spend a few moments on aeration performance, because that's a fundamental component of our technology, we compared our 1-inch, 2-inch, and 4-inch flow move pumps to a number of different types of aeration systems by using the standard aeration efficiency, which is the typical standard that's used in aeration technology. And what we found is that our pumps delivered a 40% better performance than all of these other types of systems, including diffusers, paddle wheels, surface sprays, and venturis. So, in one device, you get both pumping and aeration, which we think is quite interesting, with no moving parts and extremely energy efficient. I'm going to talk about a few particular examples of where we're installed around the world, where we have more than 100 installations of our technology. And in Canada, in an aquaculture operation, we've got a 40,000 gallon tank where we're pumping 3,600 gallons per minute. In Chile, at a company called Aqua Chile, they're the second largest salmon producer in the world. We have an 80,000 gallon tank where we're pumping 9,600 gallons per minute. And one of our installations in India is a wastewater settling tank where we transfer heavy sludge, 10,000 gallons per minute at 120, sorry, a 10,000 gallon tank at 120 gallons per minute. So our approach to the global market is quite simple. We have direct sales to key customers. We do license our technology in certain jurisdictions, and but we really have partnerships with consultants, engineers, and system designers, and primarily our distributors. And in India, of course, that's Everest Blower. So together with our colleagues at Everest, we'd like to work with appropriate companies to find customers for demonstrations and to work with customer engineers and consultants for easy integration into their existing systems. That's the end of my presentation. I'm going to hand over the presentation now to Josh, and he'll talk about how you actually apply our pumps on a regular daily basis. Actually, how he does it every day.
Yeah.
Go ahead, Josh.
Thank you, Paul, for that great presentation. So thank you all for coming to listen to our presentations. As Paul mentioned, I'm the application engineer at Flow Inertia. And so I'm going to be just running through an introduction to the application of our Airlift pumps and kind of going over some of the technical data for operating our pumps, how to set up and install our pumps, as well as maintaining our pumps. So as Paul mentioned, our Airlift pumps are a great energy efficient solution because we combine two systems into one. By using the air blower from the aeration system and injecting air into our Airlift pump, we can pump and circulate water while simultaneously aerating the water. So some applications that our Airlift pumps are great for is aeration pumping, aquaponics, fish farming system, hydroponics, heavy liquid pumping, wastewater pumping. Pretty much any application that needs to transfer fluid from A to B. It doesn't really matter what fluid that is. We've pumped heavy metals with density 6 times of water. We've also pumped sludge and slurries in the lab with highly viscous shear forces acting on the flow. Any kind of liquid our pump can handle. So what I do is I work with the customers to help size the Airlift pump for their application. And so we hand out our technical data sheet, which is here on the left, to all our customers to kind of review the performance and capacity of each size pump. And so how to kind of read our data sheet, I'll walk you through it here, is that we have the pump size just showing the 1-inch pump, the smaller pump that we offer, and the submergence ratio in this column here. I will get into a little more detail of submergence ratio in the next slides, but for now, what we need to know is that the submergence ratio is just the depth at which the Airlift pump is placed under the water level to the total length of the system. And it's just the ratio between those two numbers. And the main point right now is that the higher the submergence ratio, the better the performance of the Airlift pump. So next in our table, we highlight 2 sections. One section is looking at the best efficiency point on the curve for our Airlift pump. And the next section is looking at the maximum water flow generated for that size Airlift pump. So for a 1-inch pump at 0.9 submergence, we can read across the table in this row here, picking off the data points that we need. So for a 1-inch pump operating at 0.9 submergence, the best efficiency, we can get 8 liters per minute when injecting 0.05 liters per second. and our estimated power consumption is 0.8 watts. Then next, looking at the maximum water flow rate, we can achieve 22 liters per minute while injecting 0.5 liters per second and has an estimated power consumption of 8 watts. And so we can just read across the table for the different submergence ratios that we're operating at. So you can see 0.8, we now have 7.5 liters per minute. Oh, sorry about that. 7.5 liters per minute while injecting 0.1 liters per second of air. Next, at the maximum water flow rate, we have 18 liters per minute while injecting 0.55 liters per second of air. And we can do this across all the submergence ratios. Looking at the 2-inch pump, we can do the exact same process with the different submergence ratios. We can read across the table to see the best efficiency and the maximum water flow rate. So at 0.9 submergence, the water flow rate is 43 liters per minute while injecting 0.2 liters per second of air. Next, the maximum water flow rate is 123 liters per minute while injecting 2.7 liters per second of air. Again, we can go down the submergence ratios and read across the table. Our next size pump is now the 4-inch pump, which we fabricated out of the PVC. And so now we're kind of getting to our larger size pumps. We could see at the 0.9 submergence ratio, our best efficiency point is 216 liters per minute water flow rate and has an estimated power consumption of 16 watts. But then the maximum water flow rate is 600 liters per minute with an estimated power consumption of 204 watts. Next is our 6-inch pump. Again, we'll just look at the 0.9 submergence. Our best efficiency water flow rate is at 565 liters per minute with a 47 watt power consumption. Then the maximum water flow rate of the 6-inch pump at the 0.9 submergence is 1,450 liters per minute with an estimated power consumption of 472 watts. And then lastly, our largest size airlift pump that we offer, looking at the 0.9 submergence, the best efficiency, 1,700 liters per minute, estimated power consumption 95 watts. Maximum water flow rate is 2,685 liters per minute with an estimated power consumption of 880 watts. And as you can see across all the pumps, as you decrease the submergence ratio, the performance of our pumps decreased as well. And I will kind of now get into detail of why that's occurring. So the submergence ratio is, by definition, just the static head divided by the total length. And the total length is just made up of the static lift and the static head. The static head is just how deep you place the airlift pump at point of the injection under the water level. And the static lift is just how high above the water level you want to pump the water to. And so let's look at an example of where we keep the static head constant, say at 1 meter, and we start increasing the static lift. Well, by the definition, when we keep the static head constant and we're increasing the static lift, we're then reducing the submergence ratio. And so when we want to move water, we need to inject more air or more energy into the pump to pump the water and overcome the static lift. And so that's why when we see the submergence ratio slightly decrease, the performance decreases as well, just because we need to overcome the static lift. So a few examples of calculating the submergence ratio is, let's say the static head is 4 meters, the static lift is 1 meter, then the static head divided by the total length is just 4/5, which is 80%. Another example is, let's say the static head is 3 meters and the static lift is 2 meters. Then the static head divided by the total length is just 3/5. And so that's how we go about calculating the different submergence ratios of the systems that we work with the customers. And so the pump performance curves, as Paul showed you earlier, just kind of now highlight the table that we just previously discussed, as well as the different submergence ratios. So on the figure on the left shows our 1-inch and our 2-inch pump, while on the right is our 4, 6, and 8-inch pump. The y-axis is the water flow rate, The x-axis is the air flow rate that we need to inject into our pump. So each curve or each size pump has 5 curves, one for each of the different submergence ratios that can be used. And we just discussed how to calculate the submergence ratio. And so for each curve at the beginning, we highlight this is the best efficiency point, and at the tail end of each curve is the maximum water flow rate achieved for each size pump at each submergence ratio. So to run through a quick example of how we use these charts to size our airlift pumps, let's say we have a customer that needs 100 liters per minute of water flow rate. Well, we could just draw a horizontal line across from the water flow rate. And let's say we're operating at 0.9 submergence, we find the intersection point, and we can draw a line vertically downwards to see how much airflow we need to achieve the 100 liters per minute. So at 0.9 submergence, if we inject 0.9 liters per second of air, we can achieve the 100 liters per minute. However, let's say the system is operating at 80% submergence. Then we can continue to draw that line across from the 100 liters per minute till it intersects the 0.8 submergence line. Then from here, we draw the line downwards, and we see that we need approximately 2.35 liters per second of air at 0.8 submergence to achieve that same 100 liters per minute of air. And that's how we read our pump performance curves. Now, to kind of get into the setup of our airlift pumps, we designed our airlift pumps to work well with just PVC piping, fittings, so that it can be commonly used across the world. So the materials needed is just PVC piping, elbows, and some coupling or flexible coupling to assemble our airlift pump system. To operate the pump, we need a blower or an air source to move air through air lines that can be injected into our airlift pump through some hose bar or push connect fittings. And so to look at the air sources that can be used, one is a regenerative blower, which we typically recommend to all our customers, as this is probably the most efficient way to generate a high volume of air at low pressure. Other air sources can be an air compressor or a roots blower that generates air at high pressure. We like to recommend using the regenerative blower because most of our applications are at low pressure, so we can generate high volume at better efficiencies. And so I'm going to kind of go through air blower curve and to see how much volume of air we can generate from regenerative blower. And this is just pulled off the internet and is typical for regenerative blowers. And this corresponds to our airlift pumps, because then we can see how much air we can generate and how many airlift pumps we can hook up to one blower. So for an example, if we place our airlift pump 1 meter below the water surface, then the hydrostatic pressure in the system is going to be that 1 meter or 40 inches of the water column pressure. So similarly as our pump curves, the pressures on the y-axis instead of now the water flow rate for these air blower curves, and on the x-axis is the volume of air that can be generated. So similarly, at 40 inches of pressure, we can draw the line horizontally across to intersect the model of the regenerative blower that we're using. For this case, we're just going to use the red dotted line. We find the intersection point and we draw our line downwards to see that for this model, we can generate 80 CFM or 37 liters per second. So from here, now we can look at our pump performance curves and see that, okay, we can get 37 liters per second from the regenerative blower. How many airlift pumps can we hook up to one blower? We can put multiple 4-inch pumps, or we could just size one of our larger pumps and hook it directly up to the air blower from one blower to one airlift pump. Or like I said, we can hook multiple airlift pumps up by splitting the lines to each airlift pump. And so next, I'm going to now kind of get into the installation process of our airlift pumps. And each airlift pump comes with an engraving of the arrow pointing towards our axial injection port. And so we want to orientate the arrow pointing towards the surface of the water so that the pump is pumping water vertically upwards towards the surface. And this is just having the axial injection on top. Next, each of our pumps has threads to thread in either push connects or hose barbs to connect air lines later in the process. And next, because our pumps are designed to fit well with PVC piping, the PVC pipe can just be fitted into the top of our airlift pump. But to secure the piping and system, we suggest using flexible cupping so that later on, if we need to remove the pump, we can. And then at the top of the riser pipe, we can install a 90-degree elbow just to kind of direct the direction of the water flow coming from the riser pipe. And then next, we can also, for some, install an intake pipe at the bottom of the airlift pump. And this is just for applications generally where we want to pick up solids off the bottom of the tank. So we can place the intake pump or pipe at the bottom of the pump. And then so the inlet of that pipe is at the bottom of the tank where the solids can be suctioned up the pipe and then pumped through our airlift pump. And then lastly is just connecting the air lines from the air source into the 2 injection ports of our airlift pump. And so here's another example of our airlift pump system. We have 4 4-inch airlift pumps that were placed into a raceway system here in Canada. However, we also need to build a frame or support system that we can use pipe clamps to secure our airlift pumps to the frame. For this case was in a raceway, we could just secure our pumps to the frame and submerge it under the water. And this just helps stabilize the pumps and keep them vertically straight. However, this frame can be made out of any locally sourced material and just to secure our pumps to the frame so that they're not moving while in operation. And so we've been talking about our dual injection airlift pump. And so Paul briefly mentioned that each port has its own kind of purpose. So our axial air injection, when we inject the air, it is directed vertically upwards to enhance water lifting. And this just enhances the flow pattern that is seen inside the pipe. When we talk about slug flow, it is a large bubble that acts as a piston inside the pipe riser that will lift the water above the slug bubble. So we use the axial air injection to enhance water flow, while the radial injection is comprised of these small holes that when the air passes through creates bubbles, and this enhances the oxygenation in the water. So each port was designed specifically for their purpose, water lifting or oxygenation. So generally for most applications, we just recommend 50% of the air go through the axial port and 50% goes through the radial port. However, if customers are more concerned with increasing the liquid lifting, we'll recommend putting 75% of the air through the axial port and the remaining 25% through the radial port. However, if the customer is then more concerned with increasing the oxygenation in the water, we'll then recommend 75% of the air to go through the radial injection, and then 25% through the axial injection. And this is just simply done by placing valves on the airline. So you can close 25% so that the 75% of the air can go through the radial, or on the other end, do the exact same to the axial air injection port. And just by controlling the valves, we can control how much air is going into each port. So now to kind of get into some of the maintenance and troubleshooting, there's very little maintenance, but these are just suggestions in case problems do arise. So if there's airlift pump blockage, we just recommend shutting the system, emptying the water, and by turning on the air from the air compressor or the regenerative blower, the pressurized air will unclog any of the blockage in the airlift pump. Another one is biomass buildup. You just remove the pump, and then with a suitable cleaner, you can remove the biomass by just wiping and cleaning the pump. The next issue is maybe there's insufficient submergence ratio. So we could just shut the air off, let the water settle, and see where the static water levels, and then we can calculate the submergence ratio to see if that's where we want the submergence ratio at, and if we need to add or remove any water. Next is maybe there's insufficient airflow to the pump. So we recommend just checking the air lines, making sure there's no knots or anything obscuring the lines for getting this air to our airlift pump. Or you will maybe have to look at the air source and see if the blower is not working at full capacity. And so these are just some troubleshooting ideas, but when it comes to our airlift pumps, because of the no moving parts, there's very little maintenance. And we have also had pumps now working around the clock for 5 years, and they haven't been serviced yet. There's been no maintenance issues with our pumps. So now to look at some system configurations. So we had a customer here in Canada that came to us. They had a 151,400 liter tank. They came to us and was like, we need a turnover rate of twice per hour. So looking at the size of the tank that they needed, we figured they need a 5,300 liter per minute flow rate. So our solution was taking two 8-inch airlift pumps. And with that, then we achieved the 5,300 liters per minute, and the customer was satisfied. And this are the two 8-inch airlift pumps in a raceway system. Another system was we had a customer who was designing open net fish farms in a quarry lake, and per raceway they needed 2,400 liters per minute for a total of 14,400 liters per minute, or 14,400 liters per minute of water flow. So our solution was to use 4 4-inch airlift pumps per net. Each airlift pump had the 600 liters per minute water flow rate, and so total flow rate per net was the 2,400 liters per minute. And this was our large system here in the video, with each raceway incorporating our airlift pumps. And so, as Paul briefly mentioned, some of the airlift pump limitation is, the first is high lift pumping. So when we discuss the submergence ratio and the static lift, this is where high lift pumping can become a problem, because when you increase the static lift, then you're decreasing the submergence ratio. So when you increase the static lift to a point where the submergence ratio falls below the 50%, our pumps become inefficient and has very minimum water flow rate. Another limitation is high pressure systems, where there needs to be lots of bends and turns in the piping network. And so our airlift pumps are limited, as the pump operates off the buoyancy effect of the compressed air to move the water vertically upwards. However, our flow move airlift pumps are excellent at pumping high volume of water at low pressure, from transferring any kind of liquid from point A to point B. So thank you for your time and attention today. On the screen are just some of the highlighted benefits of our airlift pump that Paul has mentioned, and we'll both take any questions you guys have.
So
Thank you.
thanks, Josh and Paul. We do have some questions for you. So one of the questions that has come up first, Paul, is what is the technical difference between an airlift pump and an air compressor pump?
That's a great question, Kailash. I don't actually know. I'm not familiar with what an air compressor pump is. I mean, an airlift pump essentially uses the pressure of air to raise water and pump water. I've not seen that before. I'd be happy to look one up. Josh and I'll look one up, and we'll get back to you with an answer.
Okay, so we Another question is, what is the required inlet working pressure for this pump?
So I can answer that. It's just the depth at which the airlift pump is placed under the water level. So when we deal with pressures with our airlift pump, it's just a hydrostatic pressure that is by placing the airlift pump under the water level. And so that we match that pressure with the air source to be able to inject the air.
Okay. Kamlesh Kumar is asking, can this pump be used in a horizontal position?
No. Yeah, it has
No.
to be put in a vertical position.
Okay.
For,
Another question from Sampreet is, should the pump be always submerged in the liquid?
The pump doesn't necessarily have to be submerged in the liquid. The pump can be beside the tank, and piping can be brought to the pump, as shown by that one. I think you have a drawing in your presentation, Josh, where we calculate the submergence ratio. So the pump doesn't have to be in the tank, but it has to be piped into the tank, into the bottom of the tank, at the right level.
Okay.
I can. Do you
Rupesh,
want me to share that photo?
Sure, if you can.
Just if. So the pump can be placed submerged, or it can be placed on the outside of the tank, but as well as the inlet still needs to be below so that the water can fill up in the pump riser.
okay. Rupesh Kumar is asking, what about protection at the bottom of the pump? How much clearance is required?
That's a great question. So, considering that we can pump fish, there's no protection at the bottom of the pump required, unless you want to prevent something to go into the bottom of the tank, or bottom of the pump, because we do pump solids with it. So we don't put a screen at the bottom of the inlet at all.
Okay. What is the maximum head generated from this type of pump?
Josh, you want to answer that?
So it all depends on the submergence ratio. So if you want to place the pump 5 meters below the water surface level, then the maximum lift that we can achieve is 5 meters. If you want to place the pump 3 meters below the water level, then the maximum static lift is 3 meters above. And that's just because we're getting the minimum submergence ratio of 50%. So the head is just how deep you place the airlift pump, and that can be changing from each application.
Okay. Another question from Girish Panchal is, can these pumps be used for residential applications for transferring water from an underground tank to an overhead tank in buildings and bungalows?
It will all, the answer is yes. It'll be on a case by case basis. It will depend on the depth of the tank, the underground tank, and the height to which you want to lift the water. As Josh said, if you've got a tank that's 50 feet deep or 5 meters deep, then we can raise the liquid 5 meters above the surface of the water.
Josh, when you were sharing the data at the start of your presentation, one of the comments coming in from a attendee was that you have given only the water flow data. You have not shown the head. Would you please explain?
Yeah, so we show the head by showing the submergence ratio because it changes with each system and each application that we deal with. So that's why we show the submergence ratio. So each curve is the 0.9, 0.8, all the way to 0.5 submergence ratio. And so that's why our pump performance curves are different than the typical centrifugal pump curves. So we like to show the water flow rate on the y-axis, the air injection on the x-axis, and then depending on the pressure of the head, we calculate the submergence ratio, and then that's how we read our pump performance curves.
So I think this question is similar to the one earlier, but it says, what's the protection at suction?
Yeah, there isn't any.
Okay. Tushar Niralatan is asking this question, can we use these pumps in place of vertical axial tube mounted propeller pumps used for MLSS recirculation in biological treatment in wastewater treatment plants?
I think the answer is probably yes. We would have to look at each specific application in order to assess whether the pump can be used for that.
Okay. Question is, what is the O2 transfer efficiency? I think this is oxygen transfer efficiency.
Josh, you want to answer that?
So the question is, what is the
Oxygen transfer, yeah, efficiency rate.
So it's, by definition, it's just the standard oxygen transfer rate divided by the power of the airlift pump. So how much dissolved oxygen you're putting into the system divided by the power. And that's how you calculate the standard aeration efficiency.
Okay. What's the difference in terms of operation between an airlift pump and an industrial hydrocyclone?
We've not compared ourselves to an industrial cyclone. I wish we had an answer for that.
Okay. Another question is, you said these pumps can handle density 6 times more than water. How does the power consumption vary as compared to submersible pumps?
So we would so the efficiency is, when we calculate it for airlift pumps, is just we look at the water outflow for the air injection rate. So for heavier liquids, there will be more air required to move the heavier liquid, so the efficiency would slightly decrease with the higher density liquids.
Okay. Another question is it running purely on electric power or only through air pressure?
Well, actually, through air volume, the pressure required to drive our pumps is very low. The air pressure is less than 5 psi. What we need is high volume blowers. So there is electricity to run the blower, of course, but it's the airflow from the blower that runs the pump. That's the only thing that operates the pump.
Okay. What determines the choice for a submergence ratio?
Sorry, can you repeat the question?
It says, what determines the choice for a submergence ratio?
What determines the choice of the submergence ratio? Okay.
Right.
Josh?
So I had a few slides of just looking at the static head compared to the total length, which was just how deep the airlift pump was placed under the water level to how high above the water level you're trying to pump. So by taking the ratio between the depth and the total length, you can calculate the submergence ratio. And just quickly summarize, the submergence ratio is just how deep the airlift pump is submerged under the water to the total length of the system.
Okay. Mohammed Masood is saying, what is the minimum height to set a pump from the floor?
So we generally just recommend 1 diameter from the bottom of the floor.
Okay.
So very close.
Okay. A question from Joravar Singh is, if only air pressure is required, then what kind of compressor air system has to be provided? I mean, do we need to purchase air compressor separately with the pump?
You need to have an air source, an aeration source available. So if in a lot of cases, a lot of our customers already have the aeration blower as part of their system. But if they don't have an aeration blower or a regenerative blower, as Josh talked about earlier, they're very inexpensive to purchase. They're available from actually from our partner in India, from Everest Blower, and they're very inexpensive to operate in terms of kilowatts per hour.
Okay. Rajesh Jain is asking this question: what is the maximum specific gravity it can pump?
Ooh, boy.
Yeah, so we don't have an exact number, but we also have never not been able to pump anything. So we pump liquid metals, we've pumped highly viscous fluids.
What's the SG of the non-Newtonian fluids that you're pumping right now, Josh?
I don't have an exact number off the top of my head, sorry.
Yeah.
But
okay. One final question from Rupesh Kumar is, he says that water pumping from a big tank by a small diameter at height by reducing the area and increasing the pressure. Is it working in your pump?
Hmm. It doesn't, well, that's an interesting question. Our pump operates because of the air we introduce into the pump through the blower. The pressure effects taken, we'd have to look at the pressure effects as a result of a smaller diameter pump or a smaller diameter pipe in a very big tank.
So, more or less, Paul, I have taken up most of the questions that have come up during your session. So, since we don't have any more questions left, I would like to thank you and Josh for coming on an early morning in Canada to address the pump symposia. So, thank you very much for taking time out and doing this session.
Thank you so much, Kailash. We were pleased to be a part of it.
Thank you. Thanks, Paul
Fabulous.
and Josh. Uh, This brings us to the end of the pump symposia. It was our first attempt to do a technical or a technology specific session for us at Smart Water and Waste World. And we look forward to feedback from all our attendees to try to understand whether we have been able to meet the information requirements that you might have had. As I said in the morning, we have been doing a whole lot of community specific sessions like municipal or industrial. This was our first attempt at doing something for pumps. And hopefully, based on the feedback that we get from all of you attendees, we might look at trying to identify other such technologies that we could address going forward. I would like to thank all our speakers and our partners for today. Kishore Pam, Siddharth, Vineet, Kiran. We have Devdutt and Mr. Sapra from, uh, Adelino, Praveen from Andritz, and Paul and Josh from, Flonergia, Mr. Vadohane and Mr. Mistry from the Indian Pump Manufacturers Association. So, special thanks to all our speakers and a special thanks to all of you attendees for taking time out and being a part of this throughout the day. So with that and with a special thanks, I bring the pump symposia to an end, and we look forward to specific feedback from you guys. We would also like to announce the date for the IVET episode 3, that's on 15th of December. We look forward to, having multiple speakers to you on industrial wastewater and effluent treatment series. So thank you all. And with that, I bring this session to a close.